Okay, let's get started. So I'm Andy. I'm going to be talking to you about interesting characters, by which I mean I'm going to tell you about some characters, some character sets, character encodings. If you think that sounds boring, I also thought it sounded boring, but I was shocked by how interesting and quirky, annoying and exciting it is. Partly, I think, because it's just the interface, one of the interfaces between humans and computers, partly because it's harder than you think, and it's the kind of area where I found I sort of couldn't be bothered to think about it. And then when I finally kind of opened up the can and really got my head around a few of the little weird bits and bobs around it, suddenly there was this sense of satisfaction of, oh, I finally get something that before I've been avoiding thinking about. So hopefully you'll find some of these characters as interesting as I have. One slight aside before I start. I know that sometimes when I'm speaking, some people say to me, oh, how are you so calm? I just wanted to let you in on a little secret that I'm not calm at all. In fact, I've been really anxious about doing this talk for months, and I've had trouble sleeping and so on, despite the fact that I've done talks a bit like this before at ACCU and in other places. So why am I telling you that? Only because if you think there's some group of people who sort of know stuff and are fine with things, there may well be, but I'm not in it. Also, if you think you're the only person who's been struggling with dealing with this whole pandemic weirdness, you're definitely not the only person in that boat as well. Aside to side, let's get going. So I'm going to talk to you first of all about some of the ideas behind characters and character sets. I'm going to introduce you to some words that you just kind of need to memorize to be able to get the hang of it. Then I'm going to talk to you about some of my favorite characters, and then some encodings and character sets, and then we'll be done. So I encourage you to use the chat to talk to each other. Make sure you click the button that says that your messages go to everyone, not just to me. I will probably not really look at the chat. I will check in every couple of slides to make sure whether there are any questions in the Q&A section. So use that to get my attention, and feel free to chat in the chat. Having said that, I'll just check the chat now of the questions. Okay, no questions at the moment. So on to some concepts. So what I'm basically talking about today is how do you get numbers in the form of bytes, which are sometimes called octets, into brains and out of brains. So let's break that down a little bit. So we're going to be talking about numbers in the form of octets, and I'll tell you what those are. And then we're going to be grouping them into things called code units, which are like a little bit of data to do with characters. And then code units themselves will form groups which we're going to call code points, which are a number which says which character I'm talking about. And then that's going to be translated into something which we might call characters. And then you can see the arrows become a bit fluffier. So we're going to float down towards things to do with characters, glyphs, and fonts and stuff like that. And then once we've drifted a little bit further through things like eyes and screens and stuff like that, and then some other stuff we don't know about, we might end up at some meaning. And we might also go in the other direction. However, for today, we're definitely not talking about meaning. Not because we're not interested in it. And also for today, we're not going to be talking about characters, glyphs, fonts, and any way of kind of turning characters into a visual representation, because it's too hard. We're going to focus on the easier but still sometimes interestingly tricky part, which is this section. Okay, so let's start off with bytes, or what we should probably refer to as octets. So an octet is 8 bits of information. The reason why we don't use the word bytes is because in some systems, a byte can mean something else. It can even mean 9 bits in some old systems, I believe. And at some points in history, bytes were sometimes used to refer to 16-bit words and things like that. So to remove any ambiguity, octets are 8 bits of data. And if anyone tries to impress you by talking about an octet string, you might find that in some standards and stuff like that. That's not as impressive as it sounds. An octet string is a list of octets. All right, so those were the easy words. Now we get to some words that we need to memorize just to get our heads around what's going on. So first word or phrase I'm going to ask you to memorize is a code unit. So a code unit is a fixed number of octets. So a code unit isn't going to refer directly to a character, or not always. But in a particular encoding, a code unit is going to be a fixed number of octets or a fixed amount of data, normally a fixed number of octets. So for example, in UTF-8, all the code units always in UTF-8 are 8 bits, single octets. Whereas in UTF-16, all the code units always are 16 bits. So any bit of UTF-16 is always going to be made up of 16-bit code units. We might need multiple code units to talk about a character, but everything's always going to be made up of those code units. And then finally, once we've got some code units, we can group them together and we'll end up with a code point. So a code point could be made out of a variable number of code units. But once we've got a code point, we are going to be referring to something in the Unicode character set, so something that is a character. So you've got an example on the screen there of a bit of UTF-8, which is 2 code units, because code units in UTF-8 are 8 bits, but it refers to 1 character, not the same number as the number on the left. Okay, and then for the purposes of what we're talking about today, we're going to essentially consider there to be a one-to-one mapping, for most of what we're talking about at least, a one-to-one mapping between a code point and what we're going to call a character. It's definitely more complicated than that, and we'll mention some of that. But in general, for the moment at least, think of a code point as a character. For example, the character on the screen, the letter A, the code point for that is 41 in hex, and that is a Latin capital letter A. Okay, so speaking of Latin capital letter A, let's have a look at some of my favorite characters in order of complexity and also potentially in order of how much I like them. Well, certainly Latin capital letter A, much as it's, I'm okay with it. It's not that interesting. So as I said, it's 4.1 in the Unicode character set, and I'll try and be more explicit about what the Unicode character set is in a bit. And then we're going to go through a few slides where we've got this great big grid of stuff, so don't be put off by that. We're going to pick out little bits of it for different characters. But this is how to write Latin capital letter A in various different encodings. So at the top, we've got UTF-8. So to write a Latin capital letter A in UTF-8, you just have one code unit, which stands for what is written as 41 in hexadecimal or 65 in decimal. And you can also see how to do Latin capital letter A in various other encodings. For example, the second one down, UTF-16 big endian, that's one code unit, which is 2 octets, and you can see it also codes for 41. So in some abstract world, 41 in hex is the Unicode way of talking about Latin capital letter A, but also in the encoded as bytes world, you can see 41 coming up a lot. And actually, if we look at quite a lot of the other encodings that I've included down this list, they're also 41. So let's move on to something slightly more interesting, slightly more fun, which is Latin small letter E with acute. So this is one character, one code point in Unicode. It's E9 in the Unicode character set. And if you look at the second line down, you can see that in UTF-16 big endian, it's 00E9. So you can see that there's a correspondence there between the Unicode code point number and the encoding in UTF-16. However, in UTF-8, the correspondence is less direct. You can see that it actually takes 2 UTF-8 code units to write Latin small letter e with acute, not just a 1 like we had for capital letter A. I'll just check whether there's any questions. Can't see any questions so far. Feel free to ask. Very happy to stop. I should think we'll have plenty of time for questions at the end. Whether I'll be able to answer any of them is a different matter, but maybe other audience members will be. Okay, so let's move on to our next potentially slightly more complicated. Actually, no, let's go back briefly. So something else I want to point out to you. If we look back at Latin capital letter A, you can see there's an encoding about halfway down called US-ASCII, which is what we often refer to as ASCII. And you can see Latin capital letter A is 4.1 in ASCII. And you can also see just below it, 2 more encodings, ISO 8859-1 and -7. Those are often referred to as Latin 1 and Latin 7. So the capital letter A is pretty easy to write in all those encodings. If I move on to Latin small letter e with acute, that's not part of ASCII. It is part of Latin 1, and it's not part of Latin 7. So we'll talk a bit more about that later. And if I move on to Greek capital letter omega, just have a look back at the ASCII Latin 1 and Latin 7. So I'm talking about that line ISO 8859-7. So you can see that Greek capital letter omega is part of Latin 7 and not part of Latin 1 and not part of ASCII. But it's okay because you can still write it in UTF-8, and you can see that from the top line, writing the Greek capital letter omega in UTF-8 is approximately as difficult as writing small letter e with acute. It takes you 2 code units in UTF-8 to do it. And you can see it takes 1 code unit in UTF-16, which is still two octets, but this time it's 1 code unit. And you can see that the UTF-16 representation corresponds very directly with the Unicode code point number, which is that U+0389 at the very top, whereas UTF-8 doesn't correspond quite so exactly. Throughout all this, you will notice UTF-32 sitting there very calmly, looking nice and straightforward as well. Okay, so let's move on to one of my favorite character names, because I think it's really cool to be a radical mother. So this is CJK radical mother. I've had various discussions with people about what the meaning of this character is, and I don't understand the things people have said to me, so I'm not going to make any statement about whether this might mean mother or it might be combined with something else to mean mother. I don't know, but it is a character. Like I said, we're not talking about meaning. This character can be written in UTF-8 using 3 code units, as you can see at the top. Still just 1 code unit of UTF-16. 1 code unit of UTF-32 as well, because UTF-32 code units are 32-bit. Can't be written in ASCII or Latin 1 or Latin 7. Now, this is probably my favorite character name. This is presentation form for vertical right white lenticular bracket, but bracket is spelled wrong. So this is a fairly ordinary character. I presume if you want to vertically bracket something and you like a white lenticular bracket, then this would be a good character to use. But because the Unicode standard, in the Unicode standard, character names are immutable, and this standard is intended to last for all time. For all time, presentation form for vertical right white lenticular bracket will be called presentation form for vertical right white lenticular bracket spelled wrong, which pleases me a great deal. The standard also allows for aliases, so there is actually an alias for this character where bracket is spelled in the normal way. You can see again this character can be written with 3 code units in UTF-8, 1 code unit in UTF-16, but that code unit is made out of 2 octets. You'll also notice throughout this that there's an encoding. There are some encodings down the bottom I haven't talked about much, which I will talk about. This character is valid GB 18030, which, by the way, I'm simplifying slightly here by only having 1 line for it. But GB 18030 is a set of character sets, also a whole load of other standards and things that you need to follow in order to be able to sell your software to the Chinese government. And so perhaps not surprising that Chinese characters are available in GB 1803 like Radical Mother. But also worth noting that what you might think of as slightly obscure characters like presentation forms, vertical right weight lenticular bracket spelt wrong, also in at least some of the GB 1803 character sets and encodings, because to all intents and purposes, they're very similar to Unicode. I've even read statements that say that the list of characters is the same as Unicode, but I've also read statements that contradict that. So I don't know which is true. Okay, so one more example, which is like maximally complicated. Now, the reason why this is so complicated is because, as I mentioned earlier, the mapping between a character and a code point is not as straightforward as I'm trying to make it sound. So depending what you mean by character, what we can see on the screen here is one character. It's a sort of a letter I with a dot above it, with some kind of other symbol above it, and with a squiggle below it. So those are all written on top of each other, and in many senses, this is a normal character, and this is the character that's used for writing things in some cultures and languages, but it's actually formed of multiple code points. So not just multiple code units making up one code point, but multiple code points. So in order to make this, you need a Latin small letter I with ogonek, and then after that, you need to write a combining dot above, and then after that, you need to write a combining acute accent. And you can see, because of these numbers here, those three things are three different Unicode code points. When you write them next to each other like that, they should get displayed something like this. Although you'll notice I had to use an image in this slide because my browser didn't actually render them correctly. So in this case, the UTF-8 representation of all this is three code points, each of which is formed of two code units. So I'll definitely check for questions at this point. I see no questions, so I shall continue, but do ask. Yeah, you'll notice this is the first time the UTF-32 representation has got long. That's because it's now three code points. Each code point in UTF-32 is always one code unit. We've got three of them, so we've got three lots of 4 octets. One question from Roger: is there a limit? A limit on what? Please annotate your answer. Another question from Eliza. How does the compiler know how many code units it needs for a character? Yeah, so we will get to when you're writing code to read this stuff in, how you know how many code units you're going to get and stuff like that. And the different encodings have different fields around that type of thing. Is there a limit on the number of code points in a character? Oh, good question. I have no idea. I've never seen more than about 3. I don't know whether these combining characters could sort of be arbitrarily applied in some area. I don't know. Sorry. Some of these questions are probably going to go along the lines of, I don't know. There are definitely limits on the number of code units that make up a code point, and we'll get to that with the encodings. This is another one of my favorite characters, except now everyone else knows about it, so it's not as much fun as it used to be. But this is a great character to use in unit tests. So this is a pile of poo, and it represents a pile of poo. And its Unicode character set number is 1F4A9. You'll notice that there's one more number than we've been seeing in those numbers that start with U+. That's because this is like later in Unicode, or with that it is further up. It's a bigger number, which kind of indicates it came along later in the process of standardization. Yeah, it's great for unit tests because it's hard to write in your source code until you learn about all this stuff, if you want your source code to be ASCII. And a lot of your tests that assume every code point uses only one UTF-16 code unit is going to fail here, because as we can see, the UTF-16 representation of this character is two 16-bit code units to make one code point, and we'll talk about how you encode that as we go on. Yeah, so the standard way of writing these U+ numbers is U+ 4 or more numbers. So you normally have those leading zeros if the number's small, but then you just expand it out if you want more. Notice that UTF-32 is just sitting there being beautiful. One code unit per code point, like always, and that code unit directly corresponds with the Unicode code point number. Okay, no more questions yet. So another really interesting character. This is a character made of 2 code points. The first code point stands for adult, and I'm glad that we're not getting into meaning of what that is. And the second code point is emoji modifier Fitzpatrick type 6. So the Fitzpatrick scale is a skin tone, skin color scale that's been standardized in some context, and that's been adopted into Unicode as a modifier which you can add. So if you add this code point after a code point to which is relevant, like adult, the display will be of an adult with that skin color. And if you don't provide a modifier, then the skin color used for when you display adult should be a non-human color. And a lot of platforms use yellow. That's not mandated. So again, this is 2 code points, and in UTF-8, both of those code points use 4 code units. Okay, so that was some interesting characters and some introduction to like why we even need to think about how these encodings work. I now need to define some words for you. So a character set is a list of characters. So I've been going on quite a few times about the Unicode character set. So that is a list of characters. In particular, it's not an encoding. So an encoding is a way of describing how to turn, a way of turning characters into bytes or bytes into characters. And then a word that you'll hear me use later, but which is kind of irrelevant in the Unicode world, is a code page. So a code page is a character set and an encoding in a kind of grouped pair. And in particular, those would normally be quite small character sets, and maybe the encoding only fits into 1 byte or something like that. So you'd have lots of different code pages to refer to different characters. Okay, so let's talk about some real life code pages and character sets. So one that most of us have heard of, I think, is ASCII, which its full proper name is US-ASCII. This is a code page, so that means it's a list of characters and a way of encoding those characters. So there are only 128 characters in ASCII. It does include all the Latin letters, lowercase and uppercase, and numbers 0 to 9, and common punctuation. So most programming languages, not all, but most programming languages only use punctuation that's included in ASCII. It also includes some slightly odd characters. In fact, calling them characters is itself slightly odd. For example, it includes backspace. We don't know what that means. It includes something called escape. And probably the best one is that it includes something called bell, which under certain circumstances makes your computer beep, which is not really a character. You'll notice there's 128 characters in this code page. So that only uses 7 bits. Normally ASCII comes to you in 8 bits, but in order for it to be ASCII, the highest bit should be 0. So one of the reasons why this is interesting is because loads of other code pages and actually encodings are kind of based on ASCII, and they use that spare bit for other stuff. No questions so far. So let's talk about Latin 1, which should be called ISO 8859-1. So Latin 1 is another code page. It's an 8-bit code page, and it has 191 characters in it. So it's using that extra bit for some bits, but there's also some gaps in a total of 256 things you could include in a single octet. It includes all the printable ASCII characters, and an interesting little fact that's probably no use to anyone is that Latin 1 does not include the non-printable characters, so it doesn't include those control characters and things like that. Now, I would assume that 99% of programs that claim that they support Latin 1 probably also do whatever's sensible with those extra ASCII control characters, and don't really, like, I don't know what would be the correct behavior, to crash if you receive them. But yeah, technically, Latin 1 does not include those control characters, those non-printable ASCII characters. And also, there are other Latins, I presume Latin 2, and the example that I used was Latin 7. So these are multiple other code pages. So again, a code page is a list of characters and a way of encoding them. They're all 8-bit, and each different number is for a sort of characters that are suitable for a certain language or culture. So Latin 7 lets you do Greek letters, which is why we saw the omega letter was from Latin 7. So this is a nightmare. This is why everyone thinks character sets are hard, because at one point everyone was talking in code pages like this, not just the Latin ones, but things like that. And often they agree on ASCII. So you think you've got the right code page, but then later you print out an E acute when you meant an omega or something else, and you realize actually you were in the wrong code page, and there wasn't any kind of standard way of knowing what code page you were in, and everything was bad. And that's why someone decided we needed to do something about this. But before we get to that, let's talk about some of the even cooler things. So there's a couple of encodings with hilarious names. This one, I used to pronounce EBCDIC, but I'm told it's pronounced EBCDIC, or it was at the time. This is another code page, another 8-bit code page, but incompatible with ASCII. It was invented by IBM. I believe it was invented about the same time as ASCII, so you can't really claim that IBM invented it purely to lock people into their proprietary mainframe platforms, but maybe I will. It actually, EBCDIC is not just one encoding, but multiple mutually incompatible encodings. And it contains really exciting features, like the letter sequences in EBCDIC are not necessarily contiguous. So a common programming trick to ask whether something's a letter is to say, is it greater than A and smaller than Z, greater than or equal to A and smaller, less than or equal to Z. That won't work if you're using EBCDIC, because the things between A and Z may not all be letters, or I don't know, maybe A and Z are the opposite way around from what you'd expect, I'm not sure. Also, it's missing some of the common punctuation that you might frequently need. And its only possible usage these days is as a swear word. So let's move on to something better. So let's talk about the Unicode character set. So just to recap, a character set is not an encoding. So I'm not talking about UTF-8, UTF-16. The Unicode character set is a list of characters. And what's fun and cool about the Unicode character set is it's supposed to be all the characters. Now, obviously, what you mean by character comes into that. And like as a human project, collecting a list of all the characters is a big deal. So whether it's really all the characters is questionable. Certainly, there is space in the Unicode character set for characters that don't yet exist. Because the Unicode standardization process continues and more things get added. And if you keep up with these things, you'll have noticed that among things added recently were more emojis and other stuff. So in terms of the claim of including all characters, the claim that I've heard is that the Unicode character set includes all the characters you need to write all living languages, and characters that allow you to write lots of dead languages, and more are being added. It also contains a lot of emojis. Not every single emoji you might ever see on every platform, because part of the process of standardization is that people start using emojis on a few platforms, and when they're popular, they'll get added into Unicode. But certainly all the emojis I know are in Unicode. And the way you can recognize that you're talking about a character from the Unicode character set, as opposed to some encoding of a character or something else, is it's almost always written capital U plus and then some numbers, and those numbers will be hexadecimal. And as I said, there are normally 4 numbers, or there could be more if required to write the correct number. So this Unicode character set, once and for all, solves the problem, right? So there's really no need for any of the rest of the talk. Well, kinda. So the first 128 characters of the Unicode character set match ASCII exactly, which is a really sensible decision. So that means that, like we've seen, 41 hex is Latin capital letter A, but it also means that Unicode character set character number 7 is Bell, which is a consequence of a very sensible decision, but potentially not a very sensible outcome. Just checking for questions. Any questions so far? Do jump up if you want to ask. Yeah, so maybe not quite as pure as you thought, but then we're, as I talked about before, we're interfacing humans to computers. So how tidy are you expecting it to be? All right, so let's talk about some encodings. So UTF-32 is an encoding for Unicode, by which I mean it's a way of encoding into octets all the characters of the Unicode character set. And there is, as we saw in the characters before, every code point gets exactly one 32-bit code unit. And that's enough. Like the number of possible code units is more than the number of possible Unicode characters, and we'll talk about why that is in a bit. And as we saw, it's really, really straightforward to encode UTF-32. You just take the Unicode code point number and write it into a 32-bit code unit, and the same in the other direction. This is very, very simple, but it wastes a lot of space. In fact, because it can represent, the encoder could represent a lot more characters than are ever going to be allowed in Unicode, it's guaranteed to start with quite a few zeros. So it's wasteful not only if you're using certain characters. For example, if you were writing lots of Latin characters, then you'd be writing a lot of zeros. So it's very wasteful in that case, but it's even wasteful when you're using some of the more obscure characters. At one point I read that Unix or Linux was going to change to use UTF-32 because it's so nice and simple, but no way, that's never going to happen. No one uses it for anything. Feel free to contradict me, by the way. Okay, so let's get on to something more interesting, UTF-16. And just a flash forward, for those who've read the abstract of this talk, you're expected to leave this talk feeling a little bit irritated with UTF-16. So some of the good stuff is coming up. I see I've got a question. I'll just check what that is. The question is, how does UTF-32 handle endianness? So, yeah, I skimmed over that in the examples I was giving, partly because I really want to hate on UTF-16. So I'll talk about endianness under UTF-16. UTF-32 also, you need to know the endianness in order to encode and decode UTF-32. So I will talk about that quite soon while I'm hating on UTF-16. Okay, so UTF-16 is an encoding for Unicode. As I said, all the code units are 16 bits, so 2 octets. And every character in the Unicode character set can either be written with 1 code unit in UTF-16, or worst case scenario, 2 code units. And the way that works is, I don't know if you were thinking about how you would design a 2 code unit, 2 16-bit, up to 2 16-bit code unit character encodings, how would you design it? Now that I know about UTF-8, I would design it like UTF-8, we'll get onto that. But this is how UTF-16 ended up getting designed. Basically, there are 3 different possible code units. And if you look at the beginning, the first few bytes of your code unit, you can figure out which one you're looking at, and I'll show you that. So the 3 types are, it could be a single 16-bit code unit, or it could be what's called a high surrogate, or it could be what's called a low surrogate. And when you're writing a code point that takes 2 code units, you're going to need a high surrogate and a low surrogate. So basically, you've either got 1 code unit, or you've got this pair of a high and a low. So which numbers are the single code unit code points? So when I find a code unit and I look at it, how can I tell that it's going to be one of the single code unit code points? Well, basically any number from 0 up to D7FF, and any number that is bigger than E000 up to FFFF, those, if you find a code unit that is that number, then that code unit is exactly, the number in that code unit is exactly the code point number in the Unicode character set. So that's why I've written them as U plus something, which are code point numbers, but actually they're the same as the code unit. So if you find a number that is just in one of those ranges, then that number is the code point number of the character you're looking at. With me so far? So a slight diversion before we get onto the high surrogates and low surrogates, onto something called UCS2. So my understanding, and I'm probably wrong, my understanding is that during the Unicode standardization process, it was thought that the, I think 65,000 odd characters that you get from a 16-bit number was going to be enough to do all characters. And then we kind of realized at some point during that standardization process, that's not enough. But kind of as part of that process, this encoding was created called UCS2. So UCS2 was going to be the 16-bit number that represents all possible code points in the Unicode character set, because we thought that was enough. Then during the standardization process, realized that's not enough. So, but still standardized something called UCS2, or still, I'm not sure it's standardized, but there still is this thing called UCS2. And what that is only those code units that I've already talked about. So UCS2 is always 2 octets. That's why it's called UCS2. Ironically, it stands for Universal Character Set, even though you can't represent everything in the Universal Character Set with it. But yeah, all of the code points which are representable with one UTF-16 code unit are also representable in UCS2, and those are the only ones that are, and it's the same number as it is in UTF-16. So if you think UTF-16, but you're not allowed to use any of the 2 code unit characters, that's UCS2. So UCS2 is an encoding that can't do all of Unicode, but it overlaps exactly with UTF-16 on the stuff that only takes 1 code unit in UTF-16. I don't feel like I've explained that very well. So do ask if you want clarification. Yeah, so no other characters other than those ones. And that is what is known in the Unicode character set as the basic multilingual plane. So the Unicode character set is broken up into these things they call planes. And the basic multilingual plane is everything that is exactly everything that fits into UCS2. And by the way, that's, apart from emojis, that's pretty much all the characters you ever need for any living language, right? So this is not just like a Western-centric view. The basic multilingual plane includes all the Chinese and Japanese characters and others from living languages, but it's missing some emojis, so what's the point? Okay, so back to, that was a diversion onto UCS2, so back to UTF-16. But let's talk about the high and low surrogates, and here we get into some of the details of the encoding. So the high surrogates, and yes, I'm pretty sure this is not a typo on my slides, the high surrogates are the ones with lower numbers. So don't ask me why. That's what it is. But yeah, you start off with a high surrogate and then a low surrogate. You combine those two code units together and you get a code point. And this is how you combine them together. High surrogates always start with 110110 in binary, which I'm pretty sure is D800 in hex, I hope. So the stuff that I've marked in red here, this is basically just a marker to say this code unit is a high surrogate. And then this stuff here, 110111, is a marker to say this is a low surrogate. So once you've found those bytes, so this is you're reading decoding some UTF-16. You read in this byte. You have a look at the first few bits. Sorry, not reading this byte. Reading this 16-bit word. You look at the bits at the beginning of that data, and you can immediately see, okay, this is a high surrogate. Then you throw away that information, and you look at the rest of that code unit. And then you know, because you've just had a high surrogate, you know the next one's going to be a low surrogate. So you read in the next code unit, you look at the top ones just to confirm, is this a low surrogate? Yes, it is. And you collect the rest of the bits from that low surrogate, and then you combine together in order to find the code point number. Pretty sure that's on the next slide, yeah. So in order to find the code point number, you combine together the remaining bits from the high surrogate and the low surrogate. You throw away these markers which just tell you this is a high surrogate or a low surrogate. You stick these bits that I've highlighted in yellow together, the high surrogate and the low surrogate. So the reason why the high surrogate is called the high surrogate is because it contains the high bits in that sticking together. That gives you a number, but you're not quite finished, because you then have to add 10000 hex to that number that you've got out, and then you get the Unicode character set character number. So I'm going to give you a little bit of time to take that in, ask any questions. So this is why your unit tests are interesting. In order to write pile of poo in your Java code, for example, if you want your Java code to be ASCII, you have to write these two numbers with the \u thing. And your unit test will probably fail if you haven't thought of it. So you may very well be asking, but what about code points? So things in the Unicode character set. Remember I said the Unicode character set is this abstract idea of all the characters that could ever be needed. What about code points that are within that range, which are kind of marked as the high surrogate and the low surrogate in the encoding? How are we going to encode a character that's between those numbers? Because when I read in that code unit, I'm going to think it's a high surrogate, right? Well, it turns out in the perfectly pure and beautiful Unicode character set that is an abstract representation of all characters we'll ever need, there aren't any characters with those numbers because of UTF-16. Thanks, UTF-16. Thanks, Unicode. We'll live with you forever, just like the misspelling of brackets. We're going to live with this big gap in the list of the perfectly pure and beautiful list of all characters in Unicode for eternity. So UTF-16 kind of broke Unicode, at least for those of us who care about things like why is there a gap when there shouldn't be. I thought we were doing maths. But it's actually fine because there is plenty of space, depending what you mean, in the large numbers in Unicode. So the total number of characters that can be represented in UTF-16 is something near 1.2 million, I think, which doesn't sound that big. But currently, I think something like 130,000 characters are being used. And the process for adding characters to Unicode is a human process. There's a committee, and people submit proposals and things like that. So the expansion of Unicode is quite slow at the moment. So if Unicode character set continues with the same kind of purpose that it has now, and the approval process and stuff like that continues to be approximately what it is now, with no sort of automatic approval or whatever, probably that 1.1, 1.2 million characters really is enough. Now, what we always fear is some kind of order of magnitude change in what we're doing with Unicode, and at that point, suddenly that number sounds really, really small, doesn't it? Especially compared with the number of numbers you can fit into a 32-bit word, which you could, in theory, do in the UTF-32 encoding. But yeah, don't worry, it's fine. Oh, and also another thing, which we've already mentioned. What I didn't talk about when I was talking about these code units and you're reading them in is, are they being sent to me in big endian or little endian form? And it's pain, isn't it? So basically the question is which byte or which octet in each code unit comes first? So here are the two ways of representing a pile of poo in UTF-16. You'll notice the two code units always come in the same order. So the code unit, which is D8 3D, which here is written the opposite way round, will come first. That's the high surrogate. You can tell that because it's a lower number. And then the code unit, which is DCA9, comes second. So you're always going to get the code units in the order you expect. But which octet comes first in that 16-bit word is down to whether you're on a big endian or a little endian system. Okay, so I always try and find a way of memorizing things. So the way that I've tried to memorize big endian and little endian is essentially big, like in some way in my mind, big things are good. So big endian is good because it's sensible, because it's written the same way as the bits inside the byte are written, at least in like a Western writing system. So the biggest bit is on the left, and in big endian, the biggest byte is on the left as well. So the number reads off if you write it in binary in a sensible way. Whereas little endian is sort of horrible and wrong. That's the way I try and remember it. I believe this the phrase big endian and little endian comes from Gulliver's Travels, in which it's like a sort of pointless, destructive debate. So I think the implication of that is deliberate, but it is something we do have to deal with. So the way that you can tell that big endian systems are sensible is because the Amiga used them. Whereas the way you can tell little endian systems are sort of wrong is because x86 uses them. But actually it's fine, because most of the time when you're doing this stuff, you're going to be doing it over the network. Actually, maybe that's not true, but anyway, a lot of the time you're going to be doing stuff, you're going to be doing it over the network. And if you're doing it over TCP, it's well defined that TCP is big endian. So whenever you're receiving data over TCP, which would include in any kind of web or HTTP thing, you should be receiving the bytes in big endian order. And if someone's done that wrong, that's their fault. Anyway, point is, why did we get into this? Why did we use an encoding that requires us to know the endianness of the octets we're receiving, as opposed to UTF-8 where we don't? And also, why did we break Unicode just for this encoding, which, by the way, never turned out to be the good encoding that we thought? We accidentally broke Java by thinking, for the brief moment that people thought UTF-16 was a good idea, someone wrote Java. Anyway. So UTF-8, much more fun, much more exciting. So UTF-8 is another encoding for the same character set, same set of all those characters. Each code unit in UTF-8 is an octet. That's why it's called UTF-8, number of bits in a code unit. And in order to encode a code point, you need between 1 and 4 code units. So UTF-8 has some really cool properties. So it's compatible with ASCII. So what that means is that all the ASCII characters are represented in UTF-8 exactly the same as they're represented in ASCII. And this has this side effect which is that programs that only expect to receive ASCII or something like Latin 1 as a single byte encoding or code page, those programs, they tend to do operations like find the end of a line or find a null byte or something like that. And so long as those programs skip over characters in that are not in ASCII, like the ones that are higher up in the than the ASCII encoding, then those programs tend to work correctly. So if you're looking for the end of a line, which is the new line character is part of ASCII, so you're looking for a character that's the same between ASCII and UTF-8. If you're looking for the end of a line, but you've actually been fed a whole load of UTF-8, including a load of stuff that you don't understand at all, as long as you ignore those octets and just pass them through, you'll hit the new line and do the right thing, right? And so long as the next thing in the chain does understand UTF-8 and displays it correctly or something like that, the fact that you didn't know that you were skipping over a load of stuff that you didn't understand, it kind of silently works. So I don't know, is it good that programs that weren't intended for something now work correctly sometimes? I don't know. Anyway, so I think it probably is. So like Unix, very, very simple Unix programs that just replace characters or find the end of lines or something like that, are just going to work exactly right when you give them UTF-8, even though they were only written expecting Latin 1 or ASCII or something else. Another useful feature of UTF-8 is that you can recover if your stream of bytes is somehow corrupted. If you lose a byte in the middle or something like that, by examining the bytes that are coming to you, you can tell where you are within the description of a code point. You can tell what type of code unit you're looking at, and you can skip past any bad data that doesn't make sense to you, and then just find the beginning of the next code point and start again from there. This is also true of UTF-16, so long as you get whole code units. If you lose a single byte in UTF-16 or UTF-32, things are very bad. Yeah, so it's slightly more robust if you're in a situation where you might lose a byte, or bytes might get corrupted in some way. Okay, so similar to UTF-16, there are 3 different types of code unit in UTF-8. But I hope you'll agree with me that the actual the way the bits are used is sort of seems more efficient and elegant to me than UTF-16. Okay, so there are 3 types. The first type is is a code unit which represents a whole code point just on its own. So that's the part that overlaps with ASCII. And then there are other code units which say, I am the first code unit, and also I'm telling you how many more code units to expect. And then there are some other code units that just say, I'm one of the other ones, one of the later code units. So you already know how many to expect. So I'm not going to tell you. So there was a question about how something interpreting these encodings could know how many code units there are. Well, we've already answered that for UTF-32. For UTF-32, there's always 1 code unit. For UTF-16, we talked about how you can read in the first code unit, and you can tell it's either a high surrogate, in which case you expect 1 more, which is a low surrogate, or it's one of those single code points. In UTF-8, this is the way you tell. You read in 1 code unit, you can tell, oh, this is just 1 code point, or it's the first code unit of a code point that actually consists of 4 or 3 or 2, or this is a code unit that is just one of those remaining units. So let's look at some specific examples. So if we want to write Latin capital letter A in UTF-8, the leading bit, or the high bit, is 0. And that means this is a code unit that is the whole code point. So then the rest of that number is just the Unicode number for that character. So in our example, that's 41 hex. Makes sense so far? Any questions? Okay, so then the more interesting code units, you're either the first code unit of several, or you're not the first code unit. So let's have a look at Latin small letter E with acute again. So the first code unit starts 110. So the fact that it starts with a 1 indicates that this is not a single code unit code point. Then the next one says this is the first of n. And then the way we can tell that n is 2 is because we're immediately followed by a 0 there. If there were more 1s, that would mean there are going to be more code units coming. But we know because there's a 0 straight away, we're done. We know there's only going to be 2 code units in this code point. So that's the first code point. It tells you how many, code unit, tells you how many code units are left. The second code unit just starts with 1, 0. So that just means I am not the first code unit, and I'm also not one of those code units that's a single code point. I've got some more data for you. So 1, 1, 0 says there are going to be 2, and 1, 0 says here's another 1. I don't know which. And what we do is we take all the remaining bits. So those markers are now done with. So we take the remaining bits. So here we take the 3 zeros and the 2 1s and stick them on the left. And then we take the remaining bits of this, stick them on together, and then you just read off the number in binary. You don't have to do that adding that 1 0 0 0 0 thing. You just got the Unicode character number E9 straight by reading off those bits. So what I heard about UTF-8 is that, mentioning IBM again, so some people from IBM were trying to design the single octet code unit encoding for Unicode, and they sent their proposal to a couple of the people who wrote Plan 9. I forget their names. Maybe someone can tell us in the chat. And they were so appalled that they spent an evening in a bar or a cafe writing on a napkin and designed UTF-8. And that's why we've got such a beautiful, elegant. Yeah, Thompson and Pike. Thank you, Jess. Yeah, Ken Thompson and Rob Pike basically designed this over an evening in a cafe. And it gives me a great deal of respect for them because it's very beautiful. So here's an example with more code units. One of my favorite character names, again, presentation form for vertical right white lenticular bracket spelt wrong. So you can see here, this first code unit starts with 3 1s and a 0 instead of 2 1s and a 0 like the last one. So the fact that there are 3 1s here indicates there are going to be 3 code units in total. And as I was saying, the other code units just start 1 0. They don't tell you which one they are. And we get all of the other bits from our code units, stick them all together, read off the number, and that number is exactly the FE18, the code point number in the Unicode character set for this character. So I'll give you a second to just look at that. Any other questions? Cool, okay, so one more example. This is same again, but this time we've got 4 code units. So 4 leading 1s and then a 0. And then each of these other code units just has that marker to say I'm another 1. Take all the bits, stick them together, you get the code point number. Isn't it simple? So long as you're thinking about the bits, it's simple. As long as you understand that these markers at the beginning are just thrown away. All they do is identify what type of code unit is this. Now, the obvious question that may come to your mind is, why stop at 4? And the answer is UTF-16 broke everything, so you don't need more than 4 because UTF-16 can't represent more than 1.1, 1.2 million characters. But in principle, UTF-8 could extend to quite naturally up to, say, 7 or 8 code units. And that would, in principle, let you represent 2 to the power 31 characters, apparently. I haven't worked that out, but that's what someone said. And so a similar scale to what UTF-32 can represent, which is 2 to the power 32 because there's 32 bits. So both UTF-8 and UTF-32 could, in some way, in some universe, extend to cover a lot more characters. It's just that they're never allowed to because the standard says you have to do what UTF-16 can represent. Anyway, so UTF-8 is rapidly becoming the default everywhere. The World Wide Web and, as I said, TCP tend to assume it. Anytime you write HTML or something like that, and you don't specify the encoding, it's almost certainly going to be assumed to be UTF-8. Any Linux that you use recently is probably going to be working expecting UTF-8 if you don't tell it otherwise. And so eventually some of the pain that we're experiencing may go away. Well, it may take the death of Java for UTF-16 to fully go away, I don't know. Okay, so that was your fun part. Now let's get on to some of the other encodings. We're nearly at the end if you're flagging. So GB18030, as I said, is a whole bunch of standards and rules, including some encodings and character sets. It's mandatory in order to sell your stuff to the Chinese government, possibly other people in China. It's actually, I think, multiple character sets, although I've written one there. And there are several encodings. And as I said, there are conflicting accounts of whether the character set is some of the character sets overlap exactly with Unicode or only mostly. So I'm not sure what the answer is on that. But it also includes all kinds of other stuff, like you should be able to actually draw these characters and so on. Now, what I've found in practice, trying to support GB18030, an application I was working on, is that there are all these other concerns didn't concern me about the following rules and so on, and rendering. What the main job that I need to do when I was thinking about encodings is if I support the Unicode character set and the Unicode encodings, then just adding in a GB18030 encoding and decoding, which you should be able to get, you shouldn't have to write yourself, was enough. Like supporting Unicode pretty much means a GB18030 is just a matter of using the right library or something like that. So pretty straightforward. Much more difficult from other kind of social, political points of view. Another interesting one and of relevance in my work now, there is an encoding called GSM0338, which people often call GSM7, but it's not called that. And GSM7 has two interesting things about it. Number one, it's 7 bits per character, or per code unit, I should say, I guess. And secondly, it's used for SMS messages. And if you think that SMS messages allow you 140 characters, that's wrong in all kinds of ways. But in particular, if you're using GSM0338 encoding, you actually get something like 160 because you get 140 bytes and you can fit slightly more than one character in each byte in GSM7 if it's encoded the right way. So yeah, it's used in SMS messages sometimes, 7 bits per code unit. And sometimes most of the code units are just a character, and then there's a special code unit that says, oh, one of my other characters, please, and the next code unit tells you which one. So it's a very inefficient way of doing something like what UTF-8 does in a very efficient way. So basically, the characters that are supported is mostly ASCII with a bit of Latin 1 in there, and some stuff gone. And it has these extensions, like I was saying. So basically, if the first code unit is escape, which is a particular character, I think it might be 1B, then it means the next code unit you read is going to be something from the basic character set extension, which is a few extra characters like a curly bracket, stuff like that, which are just kind of missing from the first character set. So this is straight back to the kind of problems you get with Latin 1, Latin 7, and so on. You don't know, no one knows what character set extension they're using when they're using GSM. So it all goes horribly wrong. So most examples I've seen, the people are just using the basic character set extension. So not many characters can be represented by that, but that's fine, because if you're sending a text message with more interesting characters in, you're almost certainly going to be using UCS2 or another hilariously named character set, ShiftGIS. And the really fun thing about using UCS2 is that all the standards say you're using UCS2, but in actual fact, probably most of the phones are really able to support UTF-16. So if you use some of those high surrogate, low surrogate characters in your SMS message, the phone will probably handle them fine, even though the systems in between claim that they can only handle UCS2. I see there's a question. Can I give an example of how I broke unit tests with a pile of poo? I'm going to try and think of whether I can think an example at the end. I'm nearly at the end, so I'm going to run through and then try and answer that. Yeah, so if you're sending a text message that contains more interesting characters, you won't get 140 characters, you get something like 70. But it's okay because they get broken up, and then when they arrive at your phone, if they arrive at your phone, they'll get stuck back together again. So yeah, GSM7 or properly GSM 0338 is similar to ASCII. Like for example, Latin capital letter A is 41 hex. You'll notice there's no leading 0 here because it's a 7-bit encoding. But there's some things about it that are quirky. So the thing you'll notice in text messages is someone thought they were saying end of string by passing in a 0, but actually that is at in GSM 0338. So sending a 0 byte, which can happen from time to time, will end up with displaying an at on your phone screen. So if you ever got a text message that had an at in it, someone was trying to end a string at that point. So there might be some interesting stuff after it, maybe. And here's an example of that escape that I was saying. So this is a 2-code unit GSM 0338 character. So the character open curly bracket is represented by 1B, which means the next code unit is the one you should care about. It's going to be from my extension set, and then 28 says curly bracket. And the basic character set extension is really weird. It only has like something like 4 characters in it or something. No, not many. So it's very weird and inefficient. But you can get a couple of extra characters like curly brackets by doing 1B and then saying curly bracket, please. So that was your character sets, character encodings, Unicode, why we hate UTF-16, why we love UTF-8. These slides are at that URL, artificialworlds.net/presentations/interesting-characters. Other things you might want to find out about me, I'll leave on the screen while I desperately try and think of an answer to Fran's question. Okay, so how would you break unit tests with pile of poo? So the most straightforward way that you can get strings wrong in UTF-16, if you assume that there's only one code unit per character, is something like finding the length of a string or iterating through the characters in a string. So the place where I've done this the most is in Java. So in Java, if you iterate through a string in an unthinking way, you'll get the code units. So you'll get 16-bit words for each code unit of a string. So if you actually meant to iterate through the characters, and one of those characters is pile of poo, then you won't get pile of poo while you're iterating through. You'll get 2 things, one of which will be the high surrogate, one of which will be the low surrogate, and neither of them will be a valid character in Unicode, because the code unit will be one of those code units that's a high surrogate or a low surrogate. So that could be as simple as you get the length of the string wrong because you're expecting, like a string that only contains pile of poo is like 1 code point long, but it's 2 code units long, so you might get the length wrong. Or you might be iterating through those 16-bit words and just not know what to do with the first half of pile of poo. So you might crash or something. Okay, so any other questions? I'm going to see if I can see anything in the chat that I should respond to while you think of questions. Roger says they're adding hieroglyphics as well as emojis to Unicode, yeah. Oh, and Alex says JavaScript uses UTF-16. I didn't know that. Maybe we're saved because JSON uses UTF-8. Any other questions? Otherwise, I'll let you go. All right, well, thank you very much. And I'll see you around in Discord and in remote.